2 years ago, something strange started happening to our sun. It started unleashing gargantuan geomagnetic storms no one was prepared for. Auroras were seen as far south as Florida and the Bahamas, the most powerful recorded in 500 years, and satellites stopped working. But this wasn't a glitch in the matrix. Our sun was entering its most active and fiery phase, the solar maximum. This particular solar maximum, however, was almost twice as strong as scientists predicted, and we've been scrambling to understand why ever since. What we found has shaken some of our most fundamental assumptions about the sun, where its magnetic engine lives, how accurately we've been measuring it, and what's actually happening at its poles. So, what's really going on inside our star? I'm Alex McColgan and you're watching Astrum. Join me as we explore why Solar Cycle 25 caught us completely off guard, how getting closer to the sun than ever before led to model-breaking discoveries, and why the next big solar storm could spell disaster for us here on Earth.
Every 11 years, the sun goes through a solar cycle, fluctuating between a calm, dormant period known as the solar minimum and an explosive, fiery period, the solar maximum. Usually we can tell where in its cycle our sun is based on how many sunspots appear on its surface, with numbers rising and falling alongside magnetic activity. More magnetic activity means more sunspots, which also then leads to more frequent solar flares and coronal mass ejections. In other words, solar storms. But for the last few years, our star has been acting a bit weird. In 2020, the sun entered Solar Cycle 25, which turned out to be significantly more violent and turbulent than anyone expected. At its peak, 216 sunspots were observed in August 2024 alone, almost double initial predictions, and the highest number in 23 years. The million-dollar question is, why? To predict how strong a solar cycle could be, scientists rely on something called the polar field precursor. Here's how it works. As sunspots decay over the course of each cycle, their residual magnetic flux drifts towards the poles, slowly building up a strong, coherent magnetic field there.
That polar field at solar minimum is where the next cycle's activity comes from.
To measure it, scientists rely on instruments like NASA's Helioseismic and Magnetic Imager, the HMI, an instrument aboard the Solar Dynamics Observatory, which has been observing the sun from Earth's orbit and sending back countless spectacular images since 2010. So if you can measure the sun's polar fields accurately, you can predict how strong the next solar cycle is going to be. The method isn't perfect, but it's the most reliable forecasting method we have. In 2019, an international panel of experts convened by NASA and NOAA reviewed multiple separate forecasts based on the previous cycle's minimum and concluded Cycle 25 would peak at 115 sunspots, a weak, unremarkable, what you might call below average solar maximum. Cycles 22, 23 and 24 were each weaker than the last, with Cycle 24 being the weakest in the last 100 years, so such a prediction didn't seem out of place. But all that changed with a shocking realization in 2025. By building a virtual model of the HMI and running synthetic magnetic field data through it, researchers at the National Solar Observatory discovered the real HMI had only been detecting about half of the sun's true magnetic field strength at the poles. If this is true, it's no wonder our predictions were off by a long shot. But Solar Cycle 25 still came in far stronger than it should have, suggesting something deeper was at play. Since the time of Galileo, scientists have been trying to understand what drives solar activity.
Our leading theory places the answer more than 200,000 kilometers below the surface, at a boundary layer called the Tachocline. The core idea was that differential rotation at the Tachocline wound up magnetic field lines like coiled springs, generating the dynamo that drives everything we see on the sun's surface.
But in 2024, researchers from MIT, Northwestern, Edinburgh, and elsewhere challenged that assumption. By using a NASA supercomputer, they ran the most detailed solar simulations ever attempted and found that the sun's magnetic dynamo actually originates just 32,000 kilometers below the surface. Why does this matter? Well, if this is truly the case, a near-surface dynamo would be driven by magnetorotational instability, a phenomenon that occurs when a weak magnetic field connects two layers of plasma rotating at different speeds. Instead of stabilizing them, it amplifies the difference, driving turbulence that generates and sustains the magnetic dynamo. Such a mechanism could explain why consecutive solar cycles can sometimes vary so much in strength,
and would produce clear predictions that can actually be tested, unlike the old Tachocline models, which relied on poorly constrained assumptions.
And tested them we have. In 2018, NASA launched the Parry Solar Probe, which, among its mission aims, was to study the solar dynamo firsthand. After a nearly 3-year voyage, it finally arrived in April 2021, just as the sun began ramping up towards its maximum. What it's seen since then, from within the solar atmosphere itself, has transformed our understanding of the sun's active phase. On Christmas Eve 2024, the Parry Solar Probe made its closest ever approach to the sun, capturing both the corona and solar wind streaming out of it about 6 million kilometers above the surface. Careening past at almost 700,000 kilometers per hour, it's the fastest human-made object in history. But these headlines aren't even the most impressive aspects about it. Over the course of 27 orbits, the Parry probe slowly pieced together data that might have solved a decades-old mystery about our sun's outermost atmosphere. The sun's surface is a roasting 5,500 degrees Celsius, but the gaseous outermost layer of its atmosphere, the corona, is significantly hotter, ranging from 1 million degrees Celsius to a mind-melting 10 million degrees in some regions. The problem was, no one really knew why.
We understood magnetism had something to do with it, but the picture was fuzzy.
We've long known that magnetic fields accumulate, concentrate, and strengthen at the boundaries between convective cells called supergranules, and when they get powerful enough, these fields can interact with solar plasma to launch jets and nanoflares. In areas where the fields are especially strong, they can tear through the sun's surface entirely, producing sunspots and giant magnetic loops. For the most part, these loops are closed, with both ends attached to the sun. However, in some places, the loops are ripped open, extending to the edge of the heliosphere. These are known as open magnetic fields. In 1988, Eugene Parker, an astrophysicist at the University of Chicago, proposed a radical new idea. He argued that perhaps the churning, convective supergranules on the surface of the sun could not only open and close magnetic fields that stretched into the corona, but could tangle them. This would build up magnetic energy in the solar atmosphere until the field lines buckle, snap, and reconnect, transferring that stored energy into the solar atmosphere as heat. For the most part, he was ridiculed by his contemporaries and his theory was dismissed. But it wouldn't be long before a probe bearing his name would kiss the sun, and what it found vindicated his work beyond his wildest dreams.
Still, even into the dawn of the 21st century, our sun's magnetism kept behaving in surprising, unexplainable ways.
Data from ESA's SOHO mission showed us that the solar magnetic field was much more variable than we thought, and the solar wind readings taken near Earth didn't make sense. The particles showed strange compositional patterns that were inconsistent with the prevailing theory of the time that said solar wind emanated from the sun's surface. Now, in the last few years, the Parry Solar Probe has helped us connect the dots between these seemingly disparate observations. Data collected by its WHISPER camera has revealed that while the solar wind appears like a turbulent fluid from near Earth. From up close, it seems to flow outward in individual streamlets that mirror the sizes of the supergranules on the Sun's surface. With every orbit, the probe took a closer look at these streams of particles whooshing out from the Sun and found something rather peculiar. The streamlets showed the telltale signs of magnetic activity, but in the field lines, they formed a strange S-shaped structure. Called switchbacks, these phenomena are thought to occur when closed magnetic loops crash into and connect with open magnetic loops in what is known as an interchange reconnection event. These events generate heat and eject solar material into space, warming the corona and accelerating particles in the solar wind, a concept not that far off from what Eugene Parker described almost 40 years ago. Now, until recently, our model of coronal mass ejections assumed material traveled in one direction, from the Sun outward. However, during the December 2024 flyby, the Parker probe captured something else. You see this? A cloud of solar material bursts out from our star before curling inward and falling back in a U-turn formation. According to NASA, the material that makes it back to the Sun can change the solar atmosphere in subtle but important ways, which can influence how subsequent CMEs erupt. Even though we've seen hints of these inflows before, through the SOHO and stereo missions, we've never seen this process in such high resolution. With this data, scientists will be able to make precise measurements about these inflows, like their speed, shape, and size, which will ultimately help us better understand and predict solar cycles and space weather events, which could impact astronauts in space as well as the rest of us here on Earth. We'll get back to that in a bit. But Parker has shown us the Sun from the inside out, how its magnetic energy builds, erupts, and ultimately resets, governing the 11-year solar cycle. But its orbit generally keeps it in line with the Sun's equatorial plane. To truly understand solar cycles, we need to get a closer look at the hubs of the Sun's magnetic activity. And for that, we're venturing to the poles. Now, most spacecraft orbit in the ecliptic plane, the flat disk traced by the planets around the Sun. This means that for the entire history of space exploration, we've only ever seen the Sun's poles edge on, like trying to read a clock face from the side. ESA's solar orbiter was designed to fix that. Using a series of Venus gravity assists to gradually tilt its orbit, it has been climbing toward a higher and higher solar latitude with every pass. On the 23rd of March 2025, it finally crossed 17 degrees below the solar equator, locked its instruments on the Sun's south pole, and snapped the first images we've ever captured of it. And it turns out, the South Pole is a crazy, messy place hiding 3 big surprises we're only just beginning to understand. A normal magnet has clear north and south polarity, but Solar Orbiter revealed that for a short time during the solar maximum, both north and south polarity magnetic fields are present at the South Pole at the same time, tangled and intermixed. To emerge from this bubbling chaos, the Sun flips its entire magnetic field. The North Pole becomes the South, and vice versa. It's a cycle that repeats every 11 years, meaning it takes the Sun 22 years to complete an entire magnetic cycle, also known as the Hale cycle. Once the magnetic field flips, a single polarity would slowly build up and take over at the Sun's poles, settling into its most orderly configuration during the solar minimum, when the Sun is least active. Yet this was just the beginning of the story. The Solar Orbiter's onboard spectrometer, the spectral imaging of the coronal environment instrument, or SPICE, mapped how fast clumps of solar material were moving around the transition region of the polar atmosphere, a thin, irregular layer of the Sun's atmosphere where temperatures rapidly increase from 10,000 degrees Celsius to hundreds of thousands of degrees. SPICE captures the light different elements like oxygen, neon, carbon and hydrogen emit at specific temperatures, and then tracks their movement to create a velocity map of the South Pole. These measurements can then show how particles are flung out from the sun in the form of solar wind, and represent the first time we've ever traced solar wind to its source, rather than inferring it from measurements taken millions of kilometers downstream. Now, the third and final finding ties back to solar cycle 25 and why it was so much stronger than anticipated. In a November 2025 paper, solar orbiter data showed the migration of sunspot magnetic fields towards the poles might have been happening much faster than we expected. This has huge implications for forecasting future solar cycles. Remember the polar field precursor? The speed and strength of one's cycle's poleward drift determines the polar field strength at the next solar minimum, which in turn determines the strength of the next solar cycle. If the magnetic flux is arriving at the poles faster than our models predict, our estimates of future cycles are way off before we've even started.
To summarize, it seems we may have underestimated solar cycle 25 for a few reasons. Our dynamo model was flawed, our instruments only detected a fraction of the sun's actual magnetism, and the rate of flux at the poles is potentially higher than we thought.
Luckily, no massive solar flares or CMEs came our way. But if they did, what would that mean for us? Just how devastating would a massive geomagnetic storm be for us here on Earth or our astronauts in space? How can we prepare for one? On the 10th of May 2024, a huge geomagnetic storm struck Earth. These happen when the sun releases a CME, hurling 1 billion tons of magnetized plasma towards our planet. It can take this material several days to arrive, but once it does, it slams into Earth's magnetosphere, triggering a rapid and often violent exchange of energy between the solar wind and the space environment around us. Aurora blazed as far south as the Florida Keys, the Yucatan Peninsula in Mexico, the Bahamas, Jamaica, Puerto Rico, and Hawaii.
Just a month later, the sky turned faintly red in Japan, with an aurora that scientists have since found stretched far higher into Earth's atmosphere than we expected, as high as 800 meters, a sign that charged particles may carry more energy than we initially thought. But despite the breathtaking light show, geomagnetic storms can also be very dangerous because they affect Earth's magnetosphere. See, our planet is surrounded by a plasmasphere, a bubble of charged plasma that helps deflect oncoming solar material. When a geomagnetic storm hits, the pressure from the solar wind squeezes the plasmasphere inward, compressing toward Earth like a deflating balloon. After the storm passes, the plasmasphere is replenished by charged particles from the ionosphere below, which is filled with ions created when the sun's radiation strips particles in our upper atmosphere of electrons. The May 2024 geomagnetic storm, as part of cycle 25 solar maximum, was the strongest in the last 21 years. Lucky for us, JAXA's Array satellite happened to be in the right place at the right time to capture its effects on our protective magnetosphere like never before. A team led by Dr. Atsuki Shimbori of Nagoya University's Institute for Space-Earth Environmental Research collected the first continuous direct readings of the plasmasphere collapsing to low altitude during a superstorm. The team watched the outer boundary of the plasmasphere collapse from 44,000 kilometers down to just 9,600 kilometers in under 9 hours, roughly 1/5 of its usual size. This was the lowest altitude ever recorded for the plasmasphere's outer edge in the entire Arase mission era, which began in 2017. And this compression left all satellites in geostationary orbit and most in medium Earth orbit altitude severely exposed to the full force of the storm. These include most of our weather monitoring, TV broadcasting, communication satellites, and our global navigation satellite system. The peak of the storm interfered directly with GPS frequency bands,
causing position errors, data gaps, and tracking failures across global airspace, with hundreds of spacecraft affected in Europe alone. The ionospheric disturbances were so severe that sudden jumps and deviations appeared in aircraft flight tracks. Open access data from the US Space Force revealed more than 5,000 satellites had to alter their position to avoid deorbiting or crashing during the solar storm. This is especially dangerous, as a single crash can lead to thousands of pieces of space debris that can persist for decades. These, in turn, increase the risk of further crashes, creating a vicious cycle. But the most dramatic finding of all was what happened after the storm. Normally it takes 1 to 2 days to replenish the plasmasphere after a storm, but this one hit our plasmasphere so hard it took more than 4 days to bounce back. So what happened there? About an hour after the solar wind struck, intense heating near the poles drove a surge of charged particles towards the polar caps. This intense heating churned the upper atmosphere like a massive convective engine, dredging up heavier molecular gases like nitrogen and molecular oxygen from lower altitudes into regions where they don't normally exist in large quantities. Under normal conditions, the upper ionosphere is dominated by atomic oxygen ions. But when nitrogen and molecular oxygen flood into the upper atmosphere, they react with the atomic oxygen ions, reducing the concentration of those ions in the ionosphere. This is known as a negative ionospheric storm, and it's a problem. Oxygen ions play a necessary part in repopulating the plasmasphere after a geomagnetic storm like this. When a positive oxygen ion collides with a neutral hydrogen atom in the ionosphere, it takes the hydrogen's electron since it has higher affinity for electrons. This ionizes the hydrogen, which then rises along the magnetic field lines into the plasmasphere. But with fewer oxygen ions around it, the production line of hydrogen ions was cut off at the source, slowing the upward flux of plasma into the plasmasphere to a trickle. This was the first time the link between negative ionospheric storms and delayed plasmasphere recovery had been directly and conclusively established. But the sun wasn't done battering our magnetosphere just yet. A few days after the May 10th storm, a huge X-class solar flare erupted, the strongest category of solar flare. Despite its effects on our Earth-based technology, it was only ranked an 8.7 on the solar flare classification chart. The strongest flare on record, which occurred in 2003, was estimated at 45, about 5 times stronger. Yet the strongest geomagnetic storm ever was the Carrington event in 1859, for which we don't have a measured solar flare ranking. However, the storm hit Earth so violently that telegraph wires burst into flames. Today's studies estimate that if an equivalent event were to hit the United States alone, it would cause $600 billion to $2.6 trillion in damages. 20 to 40 million Americans would lose power, though it's hard to say how long for. Estimates range anywhere from 16 days to 2 years. It really depends how quickly we can fix our transformers and power grid infrastructure. And if something like this were headed our way, the scariest part is how little warning we'd have. The key factor which determines how devastating a CME would be to us on Earth is the orientation of its magnetic field.
If it points southward, that gives it the highest probability of connecting with and disrupting our own magnetic field.
The issue is, we can't measure that magnetic orientation until the solar plasma reaches the L1 Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth in the direction of the Sun, where spacecraft can remain in a hovering position relative to both bodies. And by then, we'd only have 15 to 60 minutes to respond. And while, thanks to our thick atmosphere, us Earth-based humans would be relatively protected from the lethal radiation, those who would suffer most are astronauts. If a significant solar event occurs when a crew is in space, it could raise radiation levels inside their spacecraft. too much exposure over a lifetime can increase the risk of cancer or other health disorders that could negatively impact cognition and performance. For example, this was a key consideration in NASA's recent Artemis II mission, with each astronaut being given a personal radiation tracker. Inside the Orion capsule, the hybrid electronic radiation assessor system contains 6 radiation sensors, which measured dose rates in different parts of the cabin. If radiation levels increased, Orion's onboard systems displayed warnings accompanied by an audible alarm. So what are we building to better prepare for extreme solar events that may happen in the future?
On the 23rd of January 2026, NOAA's SWFO-L1 satellite arrived at the L1 point.
The spacecraft will use top-of-the-line instruments to make real-time measurements of the solar wind, thermal plasma, and the magnetic field. Alongside this, it also carries a compact coronagraph instrument designed to detect coronal mass ejections. It's the first satellite NOAA has fully dedicated to continuous operational space weather monitoring. In addition to the SWFO-L1, NASA launched the Interstellar Mapping and Acceleration Probe, or IMAP, which is also stationed at the L1 point. Its mission is to deepen our understanding of how space storms develop and dissipate, enabling improved preparedness for adverse weather in the future by providing real-time observations of the solar wind. ESA's Vigil mission will go further still. Set to launch in 2031, it will be positioned at the L5 Lagrange point, off to the side of the Earth-Sun line. From this vantage point, it will be able to watch active sun regions rotating towards Earth before they face us, potentially extending warning times from minutes to days. On the ground, strides are being made to reduce the risks of blackouts and communication failures in the face of future solar flares. For example, implementing smart grid technologies and high voltage surge protectors in power grids, building strategic transformer reserves to quickly replace damaged infrastructure, and investing in new materials like Faraday cages around critical electronic components to deflect electromagnetic pulses induced by large storms. Slowly but surely, we are preparing. Solar Cycle 25 exposed how much we still don't know about our sun, but it also brought us several breakthroughs. The first photons of the sun's poles, a revisited theory of its dynamo, the discovery of switchbacks and how they heat the corona, and so much more. Cycle 26 is set to start anytime between 2029 and 2032. What it will bring, only time will tell, but what's certain is we'll have even more missions in space, even better instrumentation, ready and waiting to see what we can learn this time around.
Thanks for watching. We mention this a lot, but that's only because it genuinely makes a difference. Astrum runs because of people like you who take a moment to join us in what we do. So consider taking 1 minute to look at the Astrum Patreon and see if any of the tiers and rewards interest you. Every member is core to our videos, and you get to watch all of these videos completely ad-free. We truly couldn't make these videos without you. If you enjoy what we do, come join the Astrum community today.